So I'll argue that space architecture as a notion, as a discipline, as a profession, reclaims the original meaning of the term architecture for space. So the word architecture is one of those words that's been used in many ways, especially over the last quarter century, and it can mean everything from the layout of circuit boards to the design of corporations. It is generally used in English to refer to anything that has a structure and organizing framework as an approach. But I mean real architecture by this. So we define space architecture in the way you see on the screen: the theory and practice of designing and building the human environment in outer space. And several dozen practitioners came together in Houston in 2002 to develop this definition, and this is what we've begun to use since then. This is a critical step for a profession that's 10 millennia old, because the environment in space is so fundamentally different from the environment here on Earth. The presence of microgravity, or I should say the absence of gravity, the unattenuated sunlight, the lethal vacuum immediately on the other side of the wall, how you get there, how you get back, all these things are very, very different from what we find on Earth. And so therefore, as designers, that poses a fascinating, compelling challenge. This is far more than space system engineering. If you talk to space agencies or engineers who work in aerospace, they'll say, oh, we have that covered. That's what we do by systems engineering. I argue that is not the case. In fact, to me, the place where engineering, the technical side of design, and the humanistic side of design and response to design, the place where they intersect is the profession of architecture, and it does not occur by itself in aerospace engineering. So space architects are required for a future in aerospace in which people will be living in space for long periods of time. So integrating the technical and the human sensibility is what is unique about architecture. So as was mentioned, there is a new book that several of us have participated in. You see some statistics here. It's actually a very thick book, and you're welcome to look through this after the event tonight. And you can find it on Amazon. So please take a look. It's a very broad book, contributed to by 26 authors who are space architects from around the world. And it contains the topics you see listed here, having to do with orbital architecture, planet surface architecture, and architecture on Earth that is space-based. That includes spin-off as well as the design of spaceports. So some of this is real and historical. Some of it is immediately projected, that is work that NASA and other agencies are doing now. And some of it is far future. So I'm going to talk about just a couple of specific things that I've talked about in other venues, just to draw your attention to what it actually means to contemplate architecture on other worlds or architecture in space. And the first is what I'll call kitchen science. This is something that anyone who cooks is familiar with. And so I argue it will be fundamental to space architecture everywhere, although it will be different in each place. By kitchen science, I mean how the normal processes that we're familiar with on Earth work in space. And they're all different. And they are different from place to place, as I said. So there are the scientific principles here have to do with convection and mixing, how fluids, solids, and gases and plasmas operate in reduced gravity and different pressure and so forth. But the implication of these things is how we actually live, how you would cook, how you would clean, and how you would live in these places. So in 1991, I published a paper about the feasibility of resort hotels in low Earth orbit. And in that talk, I argue that until you can cook an omelet and mix a martini, you can't have a hotel. So what's fascinating is that nobody knows how to cook an omelet in microgravity. let alone in 1/6G. How similar is it to Earth gravity? Nobody knows. And I personally think that playing in those environments to discover these things is going to be fascinating, not just for those of us in the field, but for those of us not in the field. So there may be papers in the literature that have to do with convection and mixing and reduced gravity, but apart from the specialists in those fields, nobody cares. But if you can go on evening TV and show, or on the Iron Chef and show how you actually cook a meal on a space station from scratch, from raw ingredients, that I think people will find fascinating. And there's a lot to learn. These investigations must be done in space. You cannot simulate them on Earth. No laboratory on Earth can do this. And by doing these investigations, we will be defining a new way for people to live, because these environmental conditions are so fundamentally different from all of our human experience. So imagine, what do you do every day, and how would you do it on the moon, or on Mars, or in free space? This, at root, is what space architecture really is. My second topic is about what I call module architecture. We all know that space stations are made of pressure cans, pressurized modules that are attached together. They need to be launched and deployed and outfitted with equipment, and you see all cabling and wiring in the images you've seen, and maybe you'll see more later this evening. That's what we refer to as the architecture of the modules, and there's a kind of a way to do that that was pioneered by the Russians and developed further by the Americans, and now has been adopted by European module architecture, Japanese module architecture. And so all the modules on space station fundamentally are alike. But none of them is optimized for to enable development of next generation life support. So I would argue, based on the space station experience, the current experience, that our life support technology in space is still very, very primitive. And I have a list of things here that it cannot do. So for example, we have absolutely no understanding of low gravity physiology. We have quite a bit of understanding of zero gravity physiology, but none for planetary surfaces. We do not close the oxygen loop. So when we exhale carbon dioxide in space station, it's captured, and we replenish the atmosphere with new oxygen, but we have not closed that loop. Space station was designed to have that loop closed, but that was stripped out for cost reasons early on, or midway through the program. So we have not demonstrated that yet. We have no biological methods in place at all in space for example, purification of water. It's all done chemically through filtration and buffering and so forth. It's not done the way it's done on Earth by filtering water through an estuary system with plants and microorganisms that then purify the water. We don't know how to do that in space. There is no significant food production in space. We might grow a little bit of lettuce for salads, but that's very different from growing a cow. And I would suggest that based on recent experience on station, trusting that urine recycler, which gives you part of your drinking water, for a 3-year mission to Mars would be a risky proposition. There's a lot more development to do. But as I said, the architecture of modules has not been designed to support tinkering with this equipment. It's very finicky equipment, and to figure out how to do it for deeper space missions, much longer duration missions with no hope of returning the crew in the middle, we need to develop next generation systems. So I'm going to suggest for those of you who are designers in the audience to think about a module architecture which, instead of having an open space in the middle surrounded by equipment, all of which is packed like a Swiss watch into racks against the walls where you can't really get at it and play with it except to do required maintenance. How about inverting that and putting the equipment in the middle as a laboratory environment so that you can operate an experiment on the equipment itself? This has never been done in space, but I suggest that for the genuine development of systems to support space architecture, it will have to be done. The equipment itself must become the subject of experimentation. Otherwise, taking steps forward will be very slow.